Hey, hello everybody. Hey, we are on week 7. Can you believe it? Hope all of your Thanksgiving break was good. And we are at the end of chapter 6 in your book, which is Applications of Newton's Laws. And we are finally getting to the point where we're going to talk about air resistance or resistive forces that vary, that are variable. They vary with the velocity. So now there is some math. There's some math in here that you will not necessarily be familiar with, but I'm going to kind of go through part of it just so that you see where these equations are coming from. And but at the most part, don't get put off by the fact that it looks pretty complicated, because what you really need to know how to use is just the formulas at the end. So there's going to be a couple questions of the day that are going to be very, very similar to the examples in the book, which are on page 150 and 152. So those problems of the day, I'm going to do that on a separate video to use the applications of what I'm about to talk about. But there you have it. So once you go through this, you'll realize why in the earlier part we will have ignored air resistance, is because it does get fairly complicated. All right, so there are two forms of what I'm going to call variable resistance, okay? There's one that's proportional to velocity, and there's one that's proportional to velocity squared, okay? And the one that's proportional to velocity is often called the viscous component of it, the viscosity of the medium, of the fluid that an object is going to move through. Now remember, air is also a fluid. And if you've ever watched leaves blow in the wind, you will realize it flows very similarly to, for example, leaves flowing on top of a creek or even a river. So you get that fluidity of it. And the difference there is the viscosity. And so we're going to talk about model 1. And then there is one that is proportional to velocity squared. And that is one in which is often called the pressure component, because typically you're going to see that in air. Okay, so although anything moving in a fluid will experience both types, both model 1 and model 2, we end up with having the components essentially one is going to predominate. Okay, so if you were, for example, if you're moving through a fluid, let's say you're in the shallow end of a pool and you're trying to walk across that, maybe you're playing Marco Polo or something, and you go to move through that, you cannot move very fast because of all of that viscous fluid. Even though it's water, it's much more viscous than the air. So you're not going to be able to reach, or you're not going to be able to get to be going very fast. Therefore, the component that is based on velocity squared, model 2, really doesn't come into play. Okay, and if the same thing, if your fluid is so thin to be not have very much viscosity, okay, such as going through air, then you're going to be able to reach your terminal velocity, which we'll talk about in a second. And the velocity, the viscosity part, model 1, is essentially going to disappear. Now think of it this way for this model 2. If you are walking around, you're walking around in air. Now we normally don't think of the air resistance of just us walking around in air. We don't feel the same thing as if we're walking in the shallow end of a pool, because the viscosity of air and the density of air is so low. Okay, but if you think about the force that you have when you roll down your window and put your arm out the window, and if you're going 60 or 70 miles per hour, it really pulls you back, right? So it is going to be huge compared to just walking around. We don't notice what that that force is when we're walking around, because it's so much lower than the fastest we can go in that fluid, which we'll talk about, which is terminal velocity, which some of you may have heard. Okay, so in higher viscosity region, we're going to be in Model 1, and in lower viscosity models, we're going to be in Model 2. Although, okay, you could have situations, for example, like a snowflake. A snowflake, even though it's moving through air, it is going to have such a great surface area, cross-sectional area, compared to its mass, that it really is going to behave more like a Model 1. So when you're looking at questions, if it's something obvious like moving through water or oil or syrup or something like that, it's going to be Model 1. If you're going through air, then it's going to be Model 2. But if you have that kind of situation where you're not sure, the question should tell you that the resistance is proportional to velocity, which would be Model 1, or the resistance is proportional to velocity squared, and in that case, it's going to be Model 2. So those are kind of the key things in here. Now, what is something that is a non-variable resistance? Well, non-variable resistance, as we've already talked about, which is something like friction. So remember, the force of friction is mu force normal. We see no velocity. We see no velocity in this equation. And because it's not dependent on velocity, it's going to have the same resistance, whether it's going 1 meter per second or 10 meters per second. Okay, so not dependent on v. So hopefully you had enough time to copy that stuff down. But if you didn't, you can pause the video. So now we're going to talk about Model 1. Okay, and I'm going to move this back around so we are on the edge. Okay, so now really we're going to have a force, a resistant force that is equal to K1V plus K2V squared. Okay, so this would be the overall resistance. Okay, now this portion right here is really the Model 1 part, and this is really the Model 2 part. Okay, and even though they're all present in all those cases, one is going to predominate and the other one is essentially going to go to 0, so we can ignore it. And so we're just going to treat them as two separate things. And realize that when you get into the real life, even though they're both there, one is going to take over and the other one's going to disappear. Okay, so we're going to talk about this Model 1. And in your book, they don't use the prefix, or they don't use K for a constant. They're going to use, in Model 1, they're going to use B. Okay, so now if we were to have a mass, okay, a mass of M, and we just dropped it, let's say in water or oil or syrup, something like that, we're going to have the force of gravity. The force of gravity is going to pull it down, and we're also going to have some sort of resistant force, that's going to go up, okay? And the sum of the forces in the y is going to equal to ma. So we're going to have force of gravity. So I'm going to say down is positive. Force of gravity minus the resistant force is equal to ma. So now we're going to be a little more specific here. We know that the force of gravity is going to be mg. And in this case, that resistance force is equal to bv. So essentially, this b and this k are the same thing. Okay, so b or k is a constant that will change according to its size, shape, texture, medium. Okay, the medium is the type of thing that it's moving through. etc. Okay, so this B or K, okay, is going to change depending on certain characteristics. If you guys think of a cube versus a sphere dropping through the water, okay, if they're going to have a different B because they are just a different shape. And so those things we're not going to get into, but essentially they are going to be determined. They are going to be determined experimentally. And if you wanted to find out what those values would be, you could look them up for certain things like spheres. If you have a regular sphere, you could probably look that up. But if you're doing experiments on something like the shape of a car, and think about a car or a rocket, you're going to do a bunch of experiments, usually in a wind tunnel, to determine what those drag coefficients are and to think about the difference between laminar and turbulent flow, which is something for another lecture. All right, so we're going to have this, and now we can make this equation a little bit different. So now we can say mg minus bv is equal to ma. Okay, now I'd like to kind of get back to what you probably are all familiar with, or at least have heard of, which is terminal velocity. So terminal velocity. Now, we can see there, if this velocity was zero, if that velocity was zero, like when you first dropped something, okay, then its acceleration, okay, would just be g. It would be 9.8. And as this speed increased, then that acceleration would get less and less. So if b times v, for example, was to equal 9.8, okay, then you'd have whatever the mass is. If you had mg is equal to bv, then your acceleration would be equal to 0. And you could go no faster, and that would be terminal velocity. Okay, so when a is equal to 0, then you are at terminal velocity. You are at terminal velocity. Now, that doesn't mean you're not, it doesn't mean you're going 0. It means that you just can't, you're not speeding up or slowing down. Okay. Now, if we kind of plug this into, we can say mg minus bvt is equal to m times 0. And now we can say, for example, that mg divided by b is equal to our terminal velocity. So that would be one equation. And if we knew what the terminal velocity is, and sometimes that's a lot easier to figure out than the b, okay, then we could say that mg over the terminal velocity is equal to this constant b, which would tell us a lot. Now, we're going to end up coming back to this. We're going to end up coming back to this sort of at the end of this equation. All right, so now we're going to end up going with this. But we are going to divide, everything by m, okay? And now we're going to start here. So we're going to have g minus bv minus bv over m, and that's going to equal to a. And this is where the calculus part comes in. And again, if you have not taken any calculus, not a big deal. And we're going to end up getting into integrals. So again, you guys are not, even if you're in calculus, you guys not talked about integrals yet, but you will in this next quarter, okay? But we know from previous discussions that acceleration is equal to the change in velocity over the change in time. Change in velocity over the change in time. Okay, so I'm going to do a little mumbo jumbo here, and I'm going to get the change in time, dt, on this side and everything else on that side. okay? And you guys can check my work here. So I'm going to say dt is equal to dv over this g minus bv over m, okay? So hopefully we, I did that right, okay? Now, in the same way, I want to know what t is with respect to velocity, okay? So we want to develop an equation that's going to have velocity with respect to time. And if we ignore air resistance, for example, we could have something like velocity is equal to initial velocity plus at. And if we dropped it straight down, ignoring air resistance, then we would get this equation, okay? So that's really what we're after when it comes to what we're doing here. Now, remember, this is the differential of time. And if you take the integral, that is the, remember, the symbol for anti-differentiation. And so we're going to do that from 0 up to t. And in the same way, we're going to do the same thing, and we're going to go from 0 to v. And we can see that this is fairly complicated. Now, if we take the anti-differential of the differential, we're just going to end up with this variable t, okay? Now, so we know that the integral of dt is just t, but we are going to measure it from 0 up until t. So essentially, whenever we want the change, we're going to say final minus initial. So the top is the final and the bottom is the initial. Well, we know that if the initial is 0, we're just going to end up with t here, okay? But it's final minus initial, and this is going to have more of an effect when we go to the other side. All right, now we have a little problem here, is that this is pretty complicated. This is a pretty complicated situation. So oftentimes in calculus, when we have a more complicated sort of issue, what we're going to do is we're going to use a substitution, okay? So what we're going to say here to simplify this is we're going to just some variable, let's call it u, which is usually used in calculus, and we're going to say that is equal to g minus, we're going to say that is equal to g minus bv over m, minus bv over m. All right, so now what we can say here, this is still going to be here, but now we can say that this is dv over u from 0 to v. So this looks a lot better, obviously, because we're trying to simplify it. The problem that we have here is that v and u are not the same thing. And you know that when you differentiate something, we've got to have the similar variables. It's the same thing when we integrate. They've got to be of the same breadth, same variables. So now what we're going to do is we're going to take this and we're going to say, hey, if we take the differential of u, okay, then that's going to be du. And then we're going to take the differential of g, and that's just the differential of a constant, okay? So that's going to go away, and now we're going to have minus b over m dv, okay, because the negative b over m, those are just constants. So really the only thing that's a variable is the v, okay? So du is equal to negative b over m dv. And what we want is we want to get dv all by itself. So dv is going to be equal. So what we're going to do is we're going to divide both sides by b, negative b over m. And so when it comes over here, we're going to just invert that. So we're going to get negative m over b du. Okay. So now when we know what dv is, now we can substitute that in there. And we're going to get the integral of negative m over b du over u from 0 to v. This right here is a constant, so that can come on the outside. And now we're going to get negative m over b times the integral of du over u. Okay, now this this might bring back some memories of differentials. But if you have the differential of u over u, we're going to end up with a natural log, function. Okay, so when we take the integral of this, that is going to give us the natural log of the absolute value of u. Okay, and then we're also still going to have this m over, or negative m over b. Okay, so let's kind of summarize it right there. So we're going to have t from 0 to t, and this is going to equal to negative m over b times the natural log of u, absolute value of u. Okay, but this is going to be the final. Okay, the final minus the natural log. Sorry. The natural log of u initial, okay? And again, we have the absolute value. 1 second. Hey, sorry about that. I got interrupted for a few minutes here. So anyway, so where were we? Okay, so we end up having this this integral of du over u, which is the natural log of u. So now this is going to be through the terms of 0 to the v final, okay, which is going to be our final minus our initial, okay. So we're going to kind of bring this up. We're going to kind of bring this up to here. So now we remember that our u, okay, was g minus bv over m, okay. So we're going to have this minus m over b, okay, times the natural log of our u, which is going to be g minus bv, and this is going to be our v final over m. Okay, we're going to have the natural log of that minus the natural log of g minus bv initial over m. Okay, but remember our initial velocity is 0, okay? So this part is just going to go away. And now we have the natural log, we have the log minus a log, okay? And if you remember your log rules, the log minus a log is the log of the quotient, So now we can say negative m over b times the natural log of g minus bv over m all over g, okay? Now remember, this whole thing is still equal. It's still equal to t. It's still equal to t. So I'm going to bring that back here in a second. Well, I'll do it right now. So now we're going to say that this is equal to t, and now we're going to move this over to here. So we're going to divide both sides by negative m over b. Remember, when we're dividing by a fraction, it's the same thing as multiplying by the reciprocal. So this is going to be minus b over m, okay? And now this goes away. And now what we want to do is we want to get rid of this natural log. So we're going to raise this. We're going to have e to the natural log of g minus bv over m all over g. And now that means we're going to take this, raise this e to the negative bt over m. Now, e raised to the natural log just goes away, and that's equal to 1. And now we can simplify this, and we can just break these into two quotients. G over g is 1 minus bv over mg, okay? And that is equal to e to the negative bt over m, okay? And now what we want is we want to solve for V, okay? So we're going to have BV BV over mg is going to equal to 1 minus e to the negative bt over m, okay? So this quantity there, and now we're going to divide. We're going to end up dividing by b over mg, and remember, we're going to divide by b over mg. Now remember, dividing by that is the same as the reciprocal, okay? And so we're going to bring all of this, okay? And I'm just going to kind of scoot this over so I have enough room. So we're going to end up having V is equal to mg over b, mg over b. Remember, we were dividing by that, which is the same as multiplying by the reciprocal times the time of 1 minus e to the negative bt over m. All right, so this right here, this is our equation. That is our equation for the velocity with respect to time. The velocity with respect to time. Okay. Now there's going to be a couple more little variations here that I'm going to scoot this board over, and we're going to get a couple different synthesized. Sorry about that. Another more interruption here. So I would like to kind of go way back to hear what we talked about before when we talked about terminal velocity. Now, terminal velocity, remember, was mg over b, this variable. And if we look back over here, we've got mg over b. Okay, so what we can do here is say that v is equal to the terminal velocity times 1 minus e to the negative bt over m. Okay, so this is another equation. This is another equation that we have. It's the same equation. Okay, it's the same equation. It's just kind of in a slightly different form, mg over b. Now, there is another thing that you're going to find in your book, which is called tau. And tau is equal to m over b. Now, this tau is just a variable called the time constant. And this is just the Greek letter essentially for t, which is tau, and they just happen to use that. So if we know what the mass is and we know what b is, okay, then we can plug in this tau. And if we look here, we have got m over b, okay, and so we can get a third equation here. And we can say V is equal to Vt times 1 minus e to the negative t over tau. Negative t over tau. So notice that if we flip this over, we've got b over m, so that tau becomes in the denominator, and we keep the negative in there. Now, as it turns out, tau is equal to the time to reach 63.2% of the terminal velocity. And that's kind of why that tau function is kind of in there. Now, you guys have certainly dealt with natural logs when you were talking about, I know in chemistry, when you were talking about radioactive decay, probably in the beginning. And if you took Honors physics or AP physics, you're talking about first order, second order, and zero order um, reaction rates. And I think it was first order reaction rates are dealing with this natural log. So it's probably not quite as unfamiliar to you that you might seem. Again, if you did not follow all this math here, not really a big deal, because these are the equations. These are the equations that you need. And I am going to go through in a separate video on how to do the question of the day. That's just going to be different numbers. But you're going to see on Tuesday, question of the day, it's going to be dealing with this equation. And Wednesday, question of the day, is dealing with the lecture on Model 2, which I'm about to talk about. And that is perhaps a little more tangible. But then there's going to be a question of the day on that, and I'm going to go through and tell you how to do it, and you're just going to have to do it with slightly different numbers. So don't let this intimidate you. It's just about putting numbers into the right spot. Okay, so we've got this. We're going to kind of start over. We're going to kind of start over, and we're going to talk about Model 2. And I am not going to bore you. I'm not going to bore you with the details of the mathematical derivation of this. We're just going to kind of go straight to what the formula is. And again, this is in your book. So I'm going to get rid of this. And all right. So now we are back. We are back to the same thing. If we drop a mass, we're going to have our force of gravity that's going to make it go down. And again, I'm saying down is positive. Except now, instead of this resistance force being BV, it is going to be minus 1/2 d rho a v squared. Okay, and again, this is Model 2. Okay, so essentially, this d rho a, is essentially what's going to go into what would go into that K2 value. Okay, so it's going to be based on the same sorts of things that are going to be its geometry and its texture and the medium that it goes through. So let's identify these before we move on. So this is the drag coefficient. Okay, so now this drag coefficient is going to be how streamlined is the object. And I'm going to kind of go do some sort of rough sort of thing. If you had a car, okay, and you kind of had a sports car or a race car, you might have that sort of shape. So when you're moving through the air, it is going to be moving around like this, right? So we're going to call this a drag force 1. But if we also have a car, and let's take my favorite car, a VW van. Okay, so in a VW van, okay, when we have the air coming this way, we're gonna hit something that's going to be not quite so streamlined. Okay, so it is still going to go around it, but we're going to end up with a lot of turbulence here. And let's call this D2. So from a drag coefficient, okay, the drag coefficient of the VW bus is going to be greater than the drag coefficient of this, let's say, streamlined sports car. Okay, so that's what the drag coefficient also has to do with the texture of it. Okay, so moving on here, we're going to have this right here is the density of the medium. Okay, and this typically is going to be air. Okay, and air is going to have a density, that is the Greek letter rho, and that's going to be about 1.2 kilograms per cubic meter. 1.2 kilograms per cubic meter. That is more than 2.5 pounds. That's more than 2.5 pounds in a volume. In a volume that is, sorry about that. If you take a meter stick that you go 1 meter wide, 1 meter high, 1 meter deep, okay, and you just take that amount of air, that's like 2.5 pounds, which seems really strange that it would be that much. If you think about air pressure, if you take a square inch, just a square inch, and let's say on top of your head, and you took the column of air that went from where your head is all the way to outer space, that would be almost 15 pounds. That would be almost 15 pounds. And so we're walking around with a lot of weight, a lot of pressure on us, and it is due to the weight of actual air. Now, the reason we don't feel it so much is that we're constantly moving around with it. We're used to it. We've never known anything differently. And again, if we go back to the analogy of walking in water, if you walk in water, let's say a pool, you're trying to get to the other side in the shallow end, you have a lot of resistance. Okay, well, when you're walking in air, you don't feel that, but essentially it is. Okay, it's still there. Okay, so now our last variable here is going to be the cross-sectional area. Okay, area. Okay, so even though if we had a much smaller version of our VW bus, okay, and we kind of just thought about that cross-sectional area of this bus, it could be we could have that same cross-sectional area of a car that was more streamlined. So these two objects, they could certainly have different drag coefficients, but they could have the same cross-sectional area. Okay, so now let's talk about this stuff right here. And now we're going to say the sum of the forces in the y. So if we just dropped this object, we're going to have mg going down minus, because it's going in the opposite direction, 1/2 d rho a v squared, and that's equal to ma. So again, to get an idea, if this velocity was 0, right, when it started out, then this whole factor would be nothing, and you'd have mg is equal to ma, and your acceleration would equal to 9.8. Okay. Now, as this increases, then the overall acceleration is going to get less and less. Okay. And again, just like before, if we reached an acceleration of 0, okay, that means this resistance force would equal to the force of gravity, okay? And we would have mg minus 1/2 d rho a v, except now we're talking about terminal velocity, because that terminal velocity, there is no acceleration. And if we rearrange this, then we could calculate terminal velocity as equal to the square root of g minus d rho a over 2m. Okay, and that would be terminal velocity. If we, for example, wanted to know what the acceleration is, okay, then we could divide we could divide both sides by m, and we could have acceleration is equal to mg minus, actually it would be g minus d rho a v squared over 2m. And depending on what variables that they give us, we can find out, for example, we could find out what the drag coefficient is. If we knew what the cross-sectional area was, the density of the air and its terminal velocity, okay, as it flowed through, then we could manipulate that and find the drag coefficient. If we knew the drag coefficient, density, and cross-sectional area, okay, we could figure out what the terminal velocity is. And that is the sort of questions that I'm going to ask you. Okay, so this is kind of some of this math here was more than you needed, but I wanted you to see some of the math if you're in calculus, what you're going to encounter even next quarter. And if you weren't, just realize that you're going back to those equations, and you can look at the examples and realize that it's not as bad as it might seem. All right, so that is the end of week 7, lecture 1, and you will see some examples on how to do those models or those examples. Question of the day for Tuesday and Wednesday in the next video. All right, take care.